In this video, we solved the tangent line problem. In other words, we learned to compute the slope of a line tangent to a function, also called the derivative of the function at that point. So we start with the geometric intuition behind this idea, taking the limit of the slope of a secant line as the interval width becomes smaller and smaller. This allows us to then express our geometric idea for the slope of a tangent line as a limit. Next, we briefly cover some notational issues, just writing this limit in a couple different ways. And finally, we'll work two examples of computing the slope of a tangent line and finding the actual equation of a tangent line. So given some arbitrary function f of x and a point a, f of a, our main goal is to find the slope of the tangent line at a. And that tangent line is a special line that touches the curve right at the point of interest, but also has the same slope as f of x at that point. Now, to find the slope of the tangent line, we're going to revisit the idea of a secant line. A secant line for a function f of x on the interval a to b is just a line that passes through 2 points on the function at a f of a and b f of b. And we can quickly find the slope of the secant line just using the rise over run here, where the rise is f of b minus f of a, and the run or horizontal change between these 2 points, that's b minus a. So we see that the slope of the secant line is given by f of b minus f of a divided by b minus a. So there's the slope of our secant line. But now what we want to do is consider the right end of this interval to be a variable quantity. So all I've done there is replace the b with x. So the right end of the interval is at a value of x, and the vertical value corresponding to that is f of x. And now we can watch what happens to this secant line if we start computing the slope over shorter and shorter intervals. So we're letting x get closer and closer to a, and as that interval starts to become very small, we see exactly what we're looking for. That's the tangent line to f of x at x equals a. So what's the formula for the slope of a tangent line? It's just the slope of a secant line on the interval a to x, but we take the limit as x goes to a. So there's the basic solution to the tangent line problem. And I want to point out that we can also call this the derivative of f of x at x equals a. So just to clarify some notations real quick, we're going to say if f of x is a function defined on an open interval containing a, then the derivative of f of x at a can be written in two equivalent ways. The first one is the limit we've already seen, where we take secant lines on the interval a to x and apply the limit as x goes to a in order to find the slope of the tangent line. And note that we've started using the prime notation here, calling that slope f prime of a. Now there's an alternative way to write this limit that could be more convenient depending on the context of the problem. So here's our alternative definition, but it's expressing exactly the same thing geometrically. So if we look at some changes to the picture here, we're still focused on taking the limit of slopes of secant lines to find the slope of the tangent line at a, but this time we call the shrinking interval width h. So the right side x value is now a plus h, the y value corresponding to that is f of a plus h, and the rise on this interval is f of a plus h minus f of a. So to find the derivative at a, we just take the rise over run between these 2 points on a secant line, and then we take the limit as the interval width shrinks to 0, but this time we're going to write that as a limit as h goes to 0. Again, this is precisely the same geometry, just written in a little different notation. Finally, we're going to work a couple examples with our new derivative formula, one for each formulation of this limit. And in our first example, we have a function f of x equals 1/2 x squared, and we're interested in finding the slope of the tangent line, in other words, the derivative, at a equals 1. And this time we're asked to use our first definition of this limit. So we look at it as the limit as x goes to a of f of x minus f of a over x minus a. And then as a follow-up, we want to find the actual equation of the tangent line so we can plot that in our graph. So our picture is ready with a plot of the original function f of x and this single point highlighted in the graph. So that's the location a equals 1, and then f of a is f of 1, which turns out to be 1/2, and it looks about right in the graph. So let's apply our limit definition of the derivative. So what I'm looking for is the slope of this curve at x equals 1. So I have f prime of 1. This is going to be the limit as x goes to 1. So we're just replacing all the a's with 1s here, of f of x Well, that's 1 half x squared minus f of a, but a is equal to 1. So I have a 1 half times 1 squared. And then in my denominator, I have an x minus 1. So I notice that I have a 1 half on each term in the numerator, and I can just factor that out of the entire limit and write 1 half limit as x goes to 1. And then what I'm left with in that numerator is x squared minus 1, and in the denominator, x minus 1. Now I can see the numerator and denominator are both approaching 0 here. In other words, this limit is approaching the indeterminate form 0 over 0. And this is always going to happen in a limit derivative, because remember what this represents is a rise over run on an interval that's infinitesimally wide. So the rise is going to 0 and the run is going to 0. And what we need to do is find some algebraic way to simplify this to get around this indeterminate form issue. And I made an entire video dedicated to this indeterminate form issue, and I'll just post a link to that real quick at the top. But the solution in this case is to just go ahead and factor that numerator and hope that the problematic factor of x minus 1 cancels out. So what we notice about the numerator is that it's a difference of 2 squares. It's x squared minus 1 squared. So that's going to factor into x plus 1 multiplied by x minus 1. And I'll just wrap the denominator in parentheses to make this a little more clear. But x minus 1 is now a common factor that we can cancel out. So I end up with 1 half times the limit as x goes to 1 of x plus 1. This no longer has the indeterminate form issue, and I can just directly replace x with 1. That gives me a 2 in here, but there's a 1 half out in front. So the whole limit goes to 1. In other words, the slope of the tangent line at x equals 1 is 1. So we've figured out that f prime of 1 is equal to 1. And now we need an equation for this tangent line. So this derivative, that's the slope of the tangent line at the point of interest. Now we need to write down the coordinates of the point that we know the tangent line passes through. So we know the x coordinate of that point is 1, and then the y coordinate of this point, that's f of 1 again. And if we evaluate that by looking at the formula for our function, 1 half x squared, 1 half times 1 squared is just 1 half. So y is equal to 1 half. So now we have the slope of our tangent line, and we have a point that it's passing through, and we can apply the point slope formula. That's y minus y naught is equal to m times the quantity x minus x naught, and we just plug everything in there. So I have y minus 1 half is 1 times the quantity x minus 1. It's usually best to express this in slope-intercept form, so all we have to do is solve for y and simplify a little bit. So on the right-hand side, I have an x minus 1, and then I'm going to add 1 half to both sides. So I still have just a single x, and then I have a minus 1 plus 1 half. Well, that's minus 1 half. So there's the equation of our tangent line. And when we plug this equation into our plotting software, we see that it works out perfectly. This line touches our graph at only one point and shares the same slope as f of x at that point. In our next example, we have a simple rational function, f of x equals 1 over x. And again, we're interested in this location a equals 1. And this time we want to use the other formulation of this derivative limit just to get some practice using this h idea instead. So remember, h stands for the interval width, and all this expression is doing is taking the slope of secant lines, where the left end of the interval is a f of a, and the right end of the interval is a plus h f of a plus h. So this expression is really just rise over run, and then we let the interval width shrink to 0. So we're going to sub in a equals 1 so we can find f prime of 1. And we get the limit as h goes to 0 of f of 1 plus h. So I sub that into my formula for f, and I get 1 over 1 plus h, and then minus f of 1, which just gives me a 1 over 1. In my denominator, I still have this h. Now again, we're going to get an indeterminate form out of this by design, because that numerator stands for a rise, the denominator stands for a run, and our interval has infinitesimal width. So the standard algebraic manipulation here is to simplify this complex fraction. This is a fraction made out of fractions. So what we're going to do is get the numerator condensed into a single fraction, and then we simplify and hope something cancels out. So what I'm going to do is multiply the 1 over 1 by just 1 plus h over 1 plus h in order to get a common denominator here. So now both of those fractions in the numerator have a denominator of 1 plus h, so I can go ahead and subtract their numerators. So I end up with a 1 minus 1 times 1 plus h, or 1 minus 1 plus h, all divided by 1 plus h. And then that whole thing is divided by h. Now that numerator of our fraction in the numerator of the entire thing is going to simplify to 1 minus h when we distribute that minus sign, and the 1's cancel out there. I end up with just a negative h up there over 1 plus h, and then that whole thing is divided by h. So dividing a fraction by h is the same as multiplying its denominator by h, and I end up with a negative h over h times the quantity 1 plus h. And then we're relieved to see that our problematic factor of h is going to cancel out here, leaving us with a negative 1 in the numerator. So I have the limit as h goes to 0 of negative 1 over 1 plus h. And now direct substitution of h equals 0 doesn't cause any problems. It's no longer an indeterminate form, so we're allowed to do it. And when I sub that in, I end up with negative 1 over 1, which is just negative 1. So this time it turned out that f prime of 1 was equal to negative 1. And again, what that means is the slope of the tangent line at that particular point. Now we just need to find this point on the tangent line that it's passing through. And we were looking at a location of x equals 1 for this tangent line. And the y value corresponding to that is just f of 1, which is 1 over 1. And that simplifies to just 1. So the tangent line passes through the point 1, 1 with a slope of negative 1. Again, we apply the point slope formula for a line and sub in our x and y coordinates of this point. That gives me a y minus 1 is equal to m, that's the slope of negative 1, times x minus 1. And we solve for y and clean things up to put it in slope-intercept form. So I'm going to have a negative x plus 1 on the right-hand side. So there's my negative x. But then I add a plus 1 to the right-hand side in order to isolate y. So I end up with a negative x plus 2. And everything works out here. When I use a computer to plot this line, y equals negative x plus 2, I see it's doing exactly what a tangent line should do. It's passing through that point 1, 1 on the original function and has exactly the same slope as the original function at that point. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.